In this video we will discuss the relation between Einstein's coefficients, right? We have already discussed in our previous lecture about the interaction of radiation with matter. Now we will try to understand the relation between Einstein coefficients. Now, according to Einstein, the upward transition rate is equals to downward transition rate. Now the upward transition rate, as we know that it is a probability, that is P12, or in our case we can also represent this with R12 is equals to R21 for downward and R21 for downward plus R21 dash. Now we have already defined the equations for these rate of transitions, and we can represent for stimulated absorption, it is energy density, and B12 energy density, number of atom present in ground state, which is equals to the spontaneous emission, that is R21 is only depend upon the number of atom present in excited state. So here we can directly write A21 N2 plus, again here we can have B21 energy density, number of atom present in excited state, right? So I'm just going to rearrange this equation. So here B12 energy density, number of atom, that I'm going to take this towards my left hand side. We have left with B21 energy density and number of atoms is equals to A21 and 2. Now here this is common, so I'm going to take this common, and B12 and 1 minus B21 and 2 is equals to A21 and 2. Now here this energy density is equals to over B12 and 1 minus B21 and 2, right? Now here we have N2, we need to neglect this N2, so I'm going to take N2 outside this equation, B12 N1 minus B21 over N2, right? Again here this is going to be cancelled out, and again B21 we need to outside this equation, so B21 and then B12 over B21 N1 over N2 minus 1. Okay, so I'm calling this as my equation number 1. Now here we are having N1 N2, so these are the number of atoms present in state 1 and state 2. So the number of atoms can be probabilized or can be estimated by using Boltzmann relation, that is number of atom present in any state is always proportional to exponential negative to the energy of that state over kBT, right? Right now N1 over N2, that is here in our case N1 and N2 is equals to exponential minus E1 over kBT, because we are finding number of atoms for state 1 over exponential minus E2 over kBT. Now I am taking this denominator to the upside, and we have left with E2 minus E1 over kBt, right? And this is my equation number 2. Also, according to Einstein, rate of stimulated absorption is equals to rate of stimulated emission, right? So this is my equation number 3. So I am going to use equation number 2 and 3 in equation number 1 to find out the energy density. That is, energy density is equals to A21, and we are having here B21, and this B12 over B21 will be equals to 1, N1 over N2 we are going to write from equation number 2, that is exponential E2 minus E1 over kBt minus 1, right? Here again, here E2 minus E1 is what? So as we have discussed, we have two states, E1, E2, and the energy difference between these two states is E2 minus E1, and this difference has been arised due to the absorption of photons. So this is equals to h nu. Here we can write A21 over B21 exponential h nu over kBt minus 1, right? Now I am calling this as equation number 4. Again, according to Planck's, the energy density can be find out by using following relation. So the relation is energy density according to Planck's is equals to 8 pi h nu cube over c cube 1 by exponential h nu over kBt minus 1. This is equation number 5. So by relating equation number 4 and 5, we get the relation between Einstein coefficients, which is A21 over B21 is equals to 8 pi h nu cube over c cube. This is the relation between Einstein coefficients, right? This is all about the relation between Einstein coefficients. Thanks for watching this video.